Good evening and welcome to Everything Matters, Tales from the Periodic Table. Tonight is chlorine. So we're now on our 17th installment of this series. We only have, at this point, about 101 elements left to go. So we'll all be a lot older by the time we finish this series. That's good. I have job insurance. That's kind of a nice thing, too. I hope you all received your collectible card for chlorine. If you have been, how many people, let me ask this, how many people have been to previous Everything Matters, Tales from the Periodic Table? It's a long title. A couple people. So this is, other people, this is your first time. Well, I believe you might be able to fill in your set of cards if you wish back at the tables back there. I don't know if we have the complete set, but you should come back every month, and if we don't have the complete set back there, we'll print more up and we'll fill it in for you. So we hope that you'll come back for that. Also, we have the new desk calendar that is available at the Exploratorium store. And if you want a wall calendar, yes, this is crassly commercial. We have the wall calendar for Everything Matters, Tales from the Periodic Table as well. So we hope you'll check out all of the items in the store. My favorite reference, by the way, if I'm going to do store stuff, my favorite reference is this wonderful book by Theodore Gray called The Elements. Great book, by the way. So hope you check that book out. So tonight, as I mentioned, is chlorine. We're going to go for about 60 minutes total. First, I'm going to give a little talk about sort of the physical aspects of chlorine and a little bit of its history and its application where you find chlorine. And then we're going to have a couple of speakers, Emily Newman and Polly Gray from the San Francisco AIDS Foundation, and they're going to talk about how chlorine is used to sterilize needles and the implications of that on the AIDS epidemic in San Francisco. So it's going to be a really interesting talk, so stick around after I finish, because it's not done when I'm over. I'm just the introduction for Emily and Polly, so we hope you stick around for that. So chlorine is found in the periodic table. You have to go down a couple rows. Now we've actually made it all the way down to chlorine there. And so chlorine is element number 17 in the periodic table. That means there's 17 protons in the nucleus and various numbers of neutrons, which we'll talk about. Chlorine is in that far right-hand, well, not the far right-hand column, this column over here, which is called the halogen family. Chlorine, there's chlorine right there. And chlorine is part of this vertical column, and all those elements, usually in vertical columns, you find they have similar chemical properties. We've already done fluorine. We talked a little bit about how fluorine acts and the chemistry of fluorine. You can go back and look up on the web and our YouTube channel and find the fluorine talk there. Tonight's chlorine. So let's go back into history here and talk a little bit about chlorine and its discovery. It was first kind of discovered by this fellow here, Carl Wilhelm Scheele, and he studied it in in 1774. He's credited with its discovery, and he first called it, this is kind of a long name, he called it dephlogisticated muriatic acid air. Dephlogisticated because things don't burn in it, and muriatic acid, that's what hydrochloric acid was called back then, and air because it was a gas. So dephlogisticated muriatic acid air, kind of a long name. Not a good name for an element, hard to abbreviate into 2 letters, or 1 letter. So we'll get to where it was given the name chlorine in just a moment. He knew that it came from this acid, hydrochloric acid, and he isolated chlorine by reacting it with another chemical called manganese dioxide. So he took hydrochloric acid. I'm sorry, I'm using these chemical formulas. Forgive me, but for those of you, you can follow along, and I will illustrate it too. So here, I'll illustrate it with the pictures. There we go. So he took hydrochloric acid, added it to manganese dioxide, which is kind of a blackish powder, and from that reaction, he got this kind of pink precipitate, manganese chloride, water, and a greenish gas bubbled off, and that greenish gas was chlorine. So that was his reaction. It was first isolated and talked about as a pure element by this fellow, Sir Humphrey Davy. He's almost in every show because he was one of those chemists who happened to be around at the right place at the right time. And in 1809, chemists were suggesting that this gas might be an element. And Sir Humphrey Davy in 1810, just the next year, proved that it really was an element. And he called it chloros, from the Greek word for pale green, because that was the color of the gas. Now, Michael Faraday came along after that, quite a bit after, in 1823. So another couple decades later, he was the first one to actually liquefy chlorine. And so he was the first, and here's a kind of a photo of liquid chlorine. It's kind of a yellowish liquid. And if you want to come up after, I have a sample of liquid chlorine that's in a little tube that's encased in this lucite block. I'll show you a close-up of this a little bit later. And you can actually see for yourself liquid chlorine. At this temperature, it has to be about under 7 atmospheres of pressure to keep it as a liquid. So chlorine is the 23rd most abundant element in the universe. So it only makes up about 1/10,000th of the universe. So it's not super common, but it's also not super uncommon as well. It's sort of right in the middle there. It's about the 18th most abundant element in the sun, and it's also the 19th most abundant element in meteorites, the 19th most abundant element in the crust of the earth. But then, if you move to the oceans, you get a little bit of a surprise. In the oceans, it's the 3rd most abundant element after hydrogen and oxygen, which of course form water. It's the 3rd most abundant element in the oceans. It makes up an important part of the ocean and the ocean ecosystem. In us, it's actually pretty abundant in human beings because we are made up of ocean for the most part, our body. So it's actually the 10th most abundant element in human beings and makes up about 0.12% of human beings. So it's kind of important for us. It's made inside of stars. So if you look over there, chlorine, it's made inside of large stars. It's made in the cores of large stars where the temperature reaches 2.5 billion degrees. That's pretty hot. And it's made by fusing a nucleus of silicon with a helium nucleus rather. So an alpha particle, and they slam into each other and they fuse together and they make an element of chlorine. So an atom of chlorine. So you can, that's the process by which chlorine is made inside of stars. We don't make it that way here on Earth. There's no elemental chlorine on the surface of the Earth or in the atmosphere. It is so reactive that it is combined with other elements, mainly in the ocean, with, what's it combined with in the ocean? Anyone say sodium? I can't hear you up here. Yes, it's combined with sodium in the ocean to make salt. And so we have to somehow separate it from the sodium, and industrially we do that by putting salt water into one end of a reaction vessel. And you can see here that it goes in as 26% salt solution, comes out as a 24% salt solution. So something disappears there. And part of what disappears is if we attach a battery to this, and we attach the positive end of the battery over here, negative chlorine is attracted to that, and it bubbles off this electrode and comes out as a chlorine gas. And on the positive side, the negative side, positive sodium is collected on this electrode here. So this is how we get sodium as well. It comes out as solid sodium on that electrode. Now, a lot of atoms have different ways they can actually join together in the elemental form. Carbon is a good example of that. Carbon can form sheets, which we call graphite. They can form tetrahedral, pyramid-like structures, which we call diamond. And all of those things are still carbon, but they're different forms of carbon, and we call those allotropes. Chlorine only has one allotrope. That's it. 2 atoms of chlorine together. That's it. Cl2, only one allotrope. But I have to mention it anyway. Now, allotropes are different than isotopes. An allotrope is the way atoms actually build into structures, but an isotope is how many combined protons and neutrons are in the nucleus. And Chlorine always has 17 protons, but can have different numbers of neutrons. And we call the different totals of protons plus neutrons isotopes. So here are all the isotopes of chlorine, lots of them, everything from chlorine 28 to chlorine 51. That number is how many protons plus neutrons are in the nucleus. But there's only 2 of them that are stable, that are not radioactive, and that's chlorine 35 and chlorine 37. And those 2 elements, both of them, but both isotopes, occur on the in the oceans and on the Earth. They occur in different ratios. So chlorine 35 makes up about 3/4 of the chlorine on Earth, and chlorine 37 makes up about 1/4 of the chlorine on Earth. That doesn't add up to 100%. I'm going to have to check those numbers. What other interesting qualities can we look at with chlorine? Well, density, we always do density. I have a bunch of cubes up here of solid elements, not gases, that you can come up and play with later. The density of chlorine, and we're going to do it a little differently this time. We're going to say how many grams per liter of gas, because since this is a gas. And there's, if you get a liter of gas, so about a quart container of gas, that gas would weigh 3.2 grams. If it was at 0 degrees centigrade. Obviously, when you make gases hotter, they expand, and so they take up more space. So we all have to measure them all at one standard temperature. So 0 degrees C is a good temperature to do that. Let's compare that with some other gases that we've already covered. Hydrogen, much, much lighter, 0.08 grams per, 0.0809 grams per liter. Helium is actually heavier than hydrogen by double. So it's 0.17 grams per liter. Fluorine, which we've already done, and 1.6 grams per liter. Neon, about 1 gram per liter. Argon, which is next month's element. We hope you come back for argon next month. About 1.78 grams per liter. So all of those are less than chlorine. Water, if we go to grams per cubic centimeter, is about 1, but the heaviest gas that we are commonly, we use here at the Exploratorium is sulfur hexafluoride, and it's twice as heavy per liter as chlorine. And the interesting thing about sulfur hexafluoride is it's totally inert. You can breathe it in. Like helium, when you breathe in helium, your voice gets higher. This is really heavy, so when you breathe this in, your voice gets lower. So I don't have any here to show you that, but maybe at a future talk we'll do that for you. So if you come down after and take a look at these density cubes, I have a whole bunch of different elements here. We have aluminum. Well, let's go from the heavy stuff. I have tungsten. I'm going to put them all up there. Tungsten and lead and iron and copper and aluminum and magnesium, and then the last 2 are actually not elements, even though I've given them element names: plastic, PL, and maple, MA. Hey, you have to make it up. But come up and try these things. They're all pretty much the same size, except for the copper cube is a little bit bigger, and the piece of tungsten back here is a lot bigger, but it's the densest of all of them. If you're interested, that tungsten is about almost exactly the same density as gold. So you want to know what lifting a gold brick is like? Try lifting the tungsten. So let's look at the chlorine atom. It's its outer shell is almost complete. All but 1 electron in the outer shell. It has 1 space. It really wants to occupy this space. If it occupies this last space with an electron, that atom looks kind of like the next one up, argon, and it becomes inert. So it really wants to look that way. So chlorine loves to grab electrons from other elements. It's kind of a small atom, actually. I always compare them to hydrogen. So there's the size of the hydrogen atom, there's the size of the chlorine atom. They're just a little bit bigger. And its spectrum is not remarkable. Well, chlorine is up there. Let's bring the chlorine spectrum over there. There we go. And it's not a remarkable spectrum. There's some lines, some bright lines in the cyan area of the spectrum, but nothing that is going to really stand out for us here. I just wanted to show the slide. It has an interesting chemistry. It wants to grab those electrons so viciously that it combines with a lot of stuff, and you get chlorides and chlorates, and basically anything that starts with chloro or has chloro in the middle of it has something to do with chlorine. And I said I was going to show you a slide of this liquid chlorine. So here's the liquid chlorine. So This is in the pure form, but when it's combined with something like sodium, we know what that looks like. It looks like this. That's rock salt, halite, if you go find it outside. Here's a sample of, come up after, check out this beautiful sample of halite. This is from Trona, California, from a salt lake. And it occurs, of course, as we all know, it occurs in the Himalayas in salt mines, so you get this nice pink salt because it has bacteria in it that turn it pink. That doesn't make it better, does it? Or sea salt. You know, basically all salt is sea salt. No matter where, Leslie salt is still sea salt. So I don't know about going out and buying stuff specifically because it's sea salt. And again, its crystal form is actually cubic. So if you look through your hand magnifier at your table salt, this is what you're going to see. We get table salt from salt ponds. We have some beautiful salt ponds here in the South Bay. If you ever fly over them, as you come into SFO on an airplane, you get a chance to see these often through the window. They're sort of in the southern part of the bay, over on the east side of the bay. We used to have them on the west side of the bay. A lot of that has been turned back into wetlands, and I suspect that's what's going to happen to a lot of these salt ponds as well. Chemically speaking, it was first synthesized from a very simple atom, hydrochloric acid, also used industrially for virtually everything. There's other places where you know about the chemistry. You've heard of the word chlorine or chloro. For instance, this pipe is PVC pipe, polyvinyl chloride pipe. It's used everywhere everywhere really. Another place where you've heard about chlorine is something that actually was quite damaging to our atmosphere, chlorofluorocarbons, CFCs. This one here is this is Freon 12, which is dichloro-difluoromethane. And so this has 2 atoms of chlorine, 2 atoms of fluorine, and they're attached to an atom of carbon there in the middle. And this was what caused a real problem in our atmosphere. This has now been banned from manufacture and use, this particular one. So has carbon tetrachloride and all of those. And here's a wonderful graphic from our friends at NASA showing the chlorofluorocarbons and flowing down from the equator, and they get trapped over Antarctica by a polar vortex. We've heard about the one up north here, but there's also a polar vortex surrounding Antarctica that keeps those chlorofluorocarbons trapped over the continent, and those trapped chlorofluorocarbons are causing the destruction of the ozone and creating a big ozone hole. So here you can see the data from starting in 1979 of this rather large hole being formed over Antarctica. And actually, since we've banned the use of chlorofluorocarbons, that hole is now shrinking, and they expect it to actually disappear within another 50 or so years. It's actually getting smaller already. So what we've done actually has worked. So where else about chlorine? Okay, kind of an unfortunate use of chlorine has been in chemical warfare. It was the first element used in chemical warfare, the first gas ever used. Chlorine, being heavier, denser than air, tends to stay near the ground, and it was used in World War I. Well, there's several other gases that also have chlorine in them, tear gas and phosgene and mustard gas. These have been used in warfare, and all pretty early on, up till 1910. First used by the German army on April, they know the date, April 22nd, 1915 was first used in France, and the effect of this gas is devastating because this was during trench warfare, and because the gas is heavier than air, it would flow along the ground and then into the trenches where all the soldiers were, and the effects of pure chlorine gas are not pleasant at all. That was the first actual chemical warfare use and it was chlorine was the first gas used as a chemical agent. Recently brought back, apparently, in some places. Apparently Saddam Hussein used it in Iraq, and it's apparently been used in Syria recently as well. Back to more pleasant talk. It's also used for good things, too, like when you go swimming. Water purification is often done with a chlorine solution, a chlorine chemical that you can pour into a pool. You have to be kind of careful that you get the right concentration in there. Our water supply is also purified with chlorine, although it used to be chlorine. Now they've changed, they swapped out chlorine gas from water supply and are using a different chemical called chloramine, which is really kind of a modified ammonia molecule. Ammonia is NH3, but they substituted a chlorine for one of the hydrogens, and this is being used in our drinking water now to keep it biologicals from growing in our drinking water. And it's a little harder to boil away than the chlorine gas. If you have fish, you know about this, because you can't just take tap water and boil it now to get pure water. To boil the chlorine out, this doesn't boil away, so you have to actually pay attention when you have fish. And you have to use actual bottled water for your fish now. As far as disinfecting goes, or bleaching goes, the first guy to do that was this fellow, this French chemist, Claude Louis Berthollet, and he was first used chlorine gas to bleach textiles, and he did that in 1785, pretty early on. Modern bleaches he also worked on. He produced a chemical that's called sodium hypochlorite for modern bleaches, and he actually has a statue in the city that he did this in. The city is called Javel. It's outside of Paris, or it's actually part of Paris now. They actually built a statue to this chemist. Most chemists don't have statues built to them for them, and this is the molecule that he built. Very simple molecule, NaClO, sodium hypochlorite, and that's what's in all of your bleach that you use at home in Clorox. You have to use Clorox in the Bay Area because they're a local company, but in France, because he invented this in the city of Javel, it's the eau de Javel. Not a very pleasant eau, I think, but there it is. So that's all I have to say about chlorine now.